Um, well, thank you, Sweden. Very kind of you. So, hi. Can you hear me?
Yes,
Hello.
sir, we can hear you. Yes, sir,
Thank
we
you.
can hear you.
So, dear professors and all of the people here, it's a great honor for me to be giving this presentation here. And in fact, I'm very much thankful to all of you people for trusting me with your special 30 minutes in my hand in this great webinar on combating COVID. So, something that I like the most about this webinar is like this diverse range of audiences from different departments and different fields of expertise. So I try my best to stay as interdisciplinary as possible and not stay confined to any typical field. So with the greatest possible apology, I need to say that I had to turn off my camera due to some issues, and I'd love to thank Apratim very much for sharing the screen. So yeah. Great. So I'm going to talk about high-performance computing for COVID research. So I'd love to start. I think, yeah, okay. It's okay. So I'd love to start this presentation at first by introducing all of you with one of the coolest professors at our university, Dr. Rajendra Adhikari. He's the coordinator of Supercomputer Center at our university and is the assistant professor at the Department of Applied Physics. And in the picture, you can see him, and besides him, there is this HPC cluster, some different compute nodes that you can see. So at first, I'm going to talk about what high-performance computing is. Would you change the slide? You go to another slide. Thank you. So यहाँ एकजना बाजे हुनुहुन्छ. यो बाजेलाई मैले ल बाजे 100 वटा कपडा सिलाइदिनु पर्यो भनेर भन्यो भने it's going to take a lot of time for him, हैन? जस्तै उहाँले सिलाइहाल्नु भयो भने पनि फर्स्टमा एउटा कपडा सिलाउनुहुन्छ, त्यसपछि अर्को कपडा सिलाउनुहुन्छ, त्यसपछि अर्को कपडा सिलाउनुहुन्छ. It's like a series, like serial calculations, nearly a series calculation. Would you change the slide? अब त्यही कपडा 100 वटा कपडा मैले यो ठाउँमा सिलाउन दिए भने it's not going to take a very long time for them to do this, because there is work division, and this is the very principle behind high performance computing. So म यता जान्छु, फर्स्टमा रिसेप्सनिस्टले मलाई रिसिभ गर्छन् अनि त्यसपछि म उनीहरूलाई इन्स्ट्रक्सन दिन्छु अनि रिसेप्सनिस्ट यता भित्र आएर वर्क डिभाइड गरिदिन्छु. So this is the very principle behind high performance computing as well. Would you change the slide? So here's a very simple layout of high performance computing. So at first, म रिसेप्सनिस्टमा कोमा गएको जस्तै, at first we log into head node or login node. So we can log in through a secure cell terminal, and of course we can securely copy the files and upload and download the files as well. So it's a multi-user environment. For that reason, we won't be submitting any kind of jobs in the head node. So for job runnings, we'd be submitting into different compute nodes. So हाम्रो एउटा compute node मा 12 वटा CPUs हरु छ है. जस्तै रिसेप्सनिस्टले त्यो भित्रको क्लस्टर्समा गएर काम दिएको जस्तै हामीहरु would be assigning different jobs to these compute nodes. So they would be running in parallel. So for such job scheduling, there is a batch scheduling system, which we use is the Slurm file system, Slurm workload manager, which stands for Simple Linux Utility Resource Manager. So it's a multi-user environment. I mean, there would be a lot many people submitting the jobs. So there would be certain priorities over there. So people with requesting for less number of resources, there would be their jobs would be in higher priorities and for such. So we have, apart from that, we have a Lustre file system, which is a parallel distributed file system. So would you go to next slide, please? So this is what it looks like. Typically what I want to show is this the picture at the right, which is a typical Slurm files, a job submission script. So here we're requesting for 1 GPU node and 4 GPUs in it. And for every job submissions, we'd be submitting the jobs through this kind of files, which is a typical Slurm file system, job submission script. So there will be different kind of softwares that different departments would be needing. For that reason, we'd be compiling such softwares in form of modules. Would you go to the next slide, please? So these are some of the modules that we have compiled in the HPC. So GROMACS and NAMD, we usually use them for molecular dynamics simulations, typically of the range of biomolecules like DNAs, proteins, and lipids. So in the same way, if we have to do some sort of like quantum chemical calculations, like ab initio calculations, like in terms of like if we want to make calculations of energy structure calculations, a band structure calculation, density of states, or if you want to make the geometric optimization, you would be using quantum espresso and gametes. Typically, gametes would be working on the Gaussian basis set, and quantum espresso would be working on the plane wave basis sets. So likewise, we have computational for computational fluid dynamics, we have open form. So I'd be talking about it in a while. This presentation would be based on the modules that we've installed in there. So would you go to another slide? So we have a problem here. So we have a problem, and we've been working out to solve this as well. So would you go to the next slide, please? So the computing hardware resources we have was donated by CERN. We have 184 compute servers. Likewise, we have one GPU node as well, which was actually awarded to Assistant Professor Dr. Rajendra Adhikari by NVIDIA. And perhaps I need to say that it was actually due to this GPU that molecular dynamics simulation and this research have been possible. Elsewhere, like typically, about GPU, they consist of large number of arithmetic logic units and large number of threadings, due to which it can support a very intensive molecular dynamic simulations, very much GPU intensive calculations. Likewise, our technical partners are NRE, and likewise Subishu is providing the center with free internet facility. So some of the research that we've been going through is repurposing of the antiviral drugs of different families and potential inhibitors against SARS-CoV-2 targets using molecular complex dynamic simulation. Likewise, we've been working with different natural compounds as well. And altogether, we've been working with around 40 compounds. So we've been working with this molecular dynamic simulation, and their studies on structural elucidations of different orthologous proteins of different families of CoV1 and CoV2. So would you go to the next slide, please? So what is simulation? Simulation is approximate imitation of a system or a process. So typically, if we have to do any sort of such things or such sort of research in lab, that is going to be very much cost consuming and time consuming. The next thing is that we can control different parameters in it, and likewise we can do research of different at different extreme conditions. So actually this is a video that you can play, the left one. Actually this is the motion along the first eigenvector. Usually it's not that smooth. So in terms of molecular simulation, like for an example, हाम्रो बडीमा एउटा प्रोटिन छ, त्यो प्रोटिनलाई कम्प्युटर भित्र हामीहरू रेप्लिकेट गर्छौं अथवा इमिटेट गर्छौं, त्यसको मिमिक्री गराइदिन्छौं, अनि त्यो प्रोटिन हाम्रो बडीमा जस्तो सिचुएसनमा बस्छ, लाइक इट वुड बी इन अ सल्भेटेड स्टेट, हैन, हामीहरू त्यसलाई सल्भेसन त्यस्तै कन्डिसनमा गर्छौं. लाइकवाइज अब त्यसको आनी बानी बेहोरा हाम्रो बडीमा जस्तो खालको छ, त्यो आनी बानी बेहोरा पनि हामीहरू सबै त्यो प्रोटिनमा राखिदिन्छौं, and we are going to study in that way. So the figure at the right is the interaction between spike protein and the ACE protein that we have in our body. So what is the thing is, if we can halt this interaction, then disease progression can be stopped. So there would be different active sites in such forms. So if we can find a compound which can typically bind with such active sites and halt or inhibit or competitively inhibit such targets, then it can be novel. Would you go to the next slide, please? So, yeah. Hello? Yeah, great. So what I have been talking about, the next slide. Yeah, so yeah, something is coming up in the screen. All right, so typically we take the coordinates of such active sites, right? And we take that coordinate and would be complicating different kind of compounds. We'd be screening for different kind of compounds, and we'd be changing their conformations and find such compound which has the lowest binding energy, which has a very nice interaction, which can bind even in low concentration. And yeah, so there is a typical figure over there. So we can see the different non-bonding interactions like hydrogen bonds and alkaline bonds in the picture there. So yeah, they would be interacting with different active sites. So will you go to the next slide, please? Yeah, so what is, how do we do it? So every protein is made up of atoms, as we know. So each of those atoms would be having the coordinate. So we'd be having a coordinate file. We can get them out of X-ray crystallographies. So as I said, in a protein ko ani bani sabai tesma rakhnu paryo. How the protein is going to behave in our body, we are trying to replicate that. So usually in molecular dynamic simulation with Chromex and NAND, we usually would be using Newtonian physics for that, classical Newtonian physics. So the interaction between two atoms, we typically calculate their interaction energies with these equations, like for the bonding things, there would be certain sort of elasticity. Likewise, if there are three atoms, then there would be the compressibility or elasticity with the angles, and if for the planes there would be elasticity with the dihedrals. Likewise, not just with bonding things, with the non-bondings as well, like the electrostatic interactions and the van der Waal interaction. So out of this, we'd be getting the interaction energy, and from that, we can calculate the force. So force is the function of negative gradient of potential, and out of that, we can calculate the position and velocity of each of those atoms. Would you go to the next slide, please? I think the screen is lagging. Hello? Okay. So why do we need HPC for all of this? So this is a video, actually. You can play the video. So here is a system. I think this system is of the size of around 62,000 atoms. So in the red ones are the water molecules. You can play that video. Yeah. So let me take one atom over here out of all of these 62,000 atoms. So one atom, we have to calculate the like different sort of parameters, like the force acting on them, position and velocity and momentum of all of them, their energy profiles and all of those variables. Likewise, usually in molecular dynamics simulation of this range, we usually take an instant of time of around 2 femtoseconds. Usually with that ab initio, we take off the range of around 10 to the power 2 femtoseconds, but with this, we usually take 2 femtoseconds. So we're gonna be predicting what is the momentum, velocity, and force of that atom after 2 femtoseconds. Now, not just for 2 femtoseconds, suppose if we have to simulate the system for around 100 nanoseconds, then we have to make such calculations for 5 crores of times. If we have to integrate that calculation of 2 femtoseconds for 5 crores of time. And not just that, like if we have such profiles like position, force, and momentum or velocity of T1 and T2 time, we can predict that of T3 time. And likewise, we can do that. We can go on for 5 crores of times. And not just with that one atom. We have to calculate for each of those atoms, for all of these 62,000 atoms, and integrate them for 5 crores time. Like, एउटा सिपियुलाई दिने हो भने यो काम भनेको अघिको त्यो बाजेलाई ल हजारवटा कपडा सिलाउ भने जस्तै हुन्थ्यो हैन. But there would be work division in this. There is high performance computing, and for that we have GPU. So yeah, would you go to next slide, please? Hello.
Yes, I switched to next slide.
Actually, I think the screen is lagging then. Yeah. So I'm not going to talk a lot about these things because perhaps we've got some limitation of time. But the first thing is we'd be generating their topologies. We'd be applying different kind of force fields, as I said, like the different systems of force fields like CHARM and AMBER and CHROMOS and OPLSAA. So the next thing is simply what I'm going to talk about here is the beauty of simulation. Simulation is beautiful. And it's fun at the same time. So I'll be talking about some beautiful things here. Like we would be simulating, we'd be keeping such systems in a simulation box and would be solvating them because it would be in a solvated state. And we would be neutralizing it with any sort of, like if there are extra charges, like if there is positive charge, then we're going to add chloride ions in the place of that solvated water molecules. Likewise, all of the systems would be in our body would be in the minimum energy level. For that reason, we'd be setting a certain kind of energy tolerance, and we'd be minimizing the systems. Like there would be different sort of stereo classes and all of them. Another thing is we'd be equilibrating the system. Like we'd be using different kind of thermostats and stats to be controlling such thermodynamic parameters. Likewise, we'd be then running making the production run. So would you go to the next slide? Yeah, I think the screen is lagging. By the way, another beautiful thing that I want to talk about is this periodic boundary condition. Like for an example, that you can see this, just take one box in the middle. So there are different sort of atoms in there, right? So we are simulating in a box. So the way the atoms in the middle of this box would be interacting would be different than the way they would be interacting at the surface. So we have to solve that problem. So a beautiful way, I like it the most in simulations. And what we do is we would be propagating that box, creating a periodic image all over infinity. So the periodic boundary condition is like if one atom moves into the other box, then other atom would be moving into that box. So yeah, so another slide please. So there are different parameters that we have to govern and take care of, because parameters are very important for simulations. Likewise, as I said, like there would be different kind of algorithms. Like as I said, if we have the position and profiles of T1 and T2 time, we can integrate it. We can calculate and predict the motion of that atom in T3 time. Likewise, there would be different sort of integration algorithms like leapfrog algorithms and velocity Verlet algorithms and for such. Runtime as well is very important to control the timings, and like all of those things would be going to be written as in the form of trajectories. So in what duration are we going to write such trajectory files? Likewise, different sort of bonding parameters and different sort of short range interactions. Like we'd be creating a sort of a cutoff range for that. Likewise, for long range interactions like electrostatic interactions, we'd be using the methods of fast Fourier transforms for that. Likewise, we'd be controlling different sort of thermodynamic parameters through barostats and thermostats, and we'd be at first generating the velocity through the Maxwell-Boltzmann velocity distribution. Would you go to the next slide, please? Yeah, so I'm going to be talking about this thing. Like if you have to be talking about a protein, then the proteins are made of amino acid sequence, right? So such amino acids would be forming and coiling and would be forming different sort of secondary structures. So there are different sort of secondary structures, like as you can see, like alpha helix turns and beta sits and B breezes and all of them. So as I'm saying, why are we trying to simulate in this dynamics? Like it's not static. Like one residue is not going to stay in one conformation all the time. For if we have to simulate them for 1 nanosecond or 100 nanoseconds, then the secondary structures are going to change. So this is the diversity in the very right picture. You can see the diversity of, like in the y-axis, there are different residues, and in the x-axis, you can see with the progression of time, how are the secondary structures changing. Apart from that, I want to talk about root mean square deviation, which is like, we are trying to simulate that protein for 100 nanoseconds. Then the very first structure, how is it differing from that very first structure? If such kind of deviation is very, not changing so much, then we can say that the system is quite stable. If it's so much moving, then we can say that it's quite unstable. So I think I forgot labeling that thing in this graph. Like you can see the purple one in this graph, it's varying very much, right? and the green one is not so much varying, so it's quite a stable system. Would you go to another slide, please? Okay, so we've been talking about like the complex of ligand and protein. Suppose the ligand is bound to a protein and inhibiting some other sort of targets. So what is their interaction like? So one way to calculate that is like the distance between the ligand and the protein. So in a dynamic system, if you simulate that for, let me say, for around 100 nanoseconds, then it's not going to stay on the same place all of the time, right? It's going to move. Like for sometimes, if you have to see in this, the first graph at the top left corner, then the green one, so that's varying so much with the progression of time, while the pink one, it's not so much varying. This is in terms of root mean square deviation. So the one in the top right corner, so this is the free energy profile of the protein along the time progression. So typically, like with the evolution of time, the protein would be going to different sort of conformation with high energy states and low energy states. So the one with the green here, the blue one is the energy minimum position. So we can get the positions or the time frame, extract such time frames out of this. In the x-axis, there is this RMSD and the root mean square deviation. And in the y-axis, there is this radius of gyration. Now we can say, like typical, what is the energy minimum structure, and we can extract that, and typically that is the kind of structure that we would be using for docking of the proteins, that typical. So the other kind of analysis method would be this root mean squared fluctuation, like suppose there is an unbound state of a protein and a bound state of a protein. So in the x-axis here, if you have to see in the lowermost left corner, then in the x-axis we have different residues of a protein, and in the y-axis we have this root mean square fluctuation. We are trying to say that what sort of fluctuation, by what degree is each of those residues fluctuating with the progression as the average value of the time. Like there is an active site, suppose, then the unbound state would be with a very high fluctuation, while at the same time the bound state would be less fluctuating. So the other thing that I want to talk about, one of the results, is this radius of gyration. It's very important means for studying protein folding, like with the progression of time. Like for an example, if you would gradually increase the temperature of the system, then it would gradually be unfolding, right? So with what degree is it unfolding? We can say it in terms of the radius of gyration, the radius of the protein. So would you go to the next slide, please? So there are several more sort of analysis that we can do, but I'm just talking about these things for now. So another mean is, suppose we have ligand and a protein bound with each other, and there be a certain sort of interaction between them. So how can we say that how much is are those things interacting? Is by pulling them. So one more approach in this drug, this kind of simulation system that we use in drug discovery is like calculating the interaction energy by a pulling simulation. Like we would be setting a certain force constant and constrain the position of the protein, and we would be, with certain force constant, we'd be pulling the ligand with a certain along the certain reaction axis, or this reaction coordinate axis. So we'd be calculating we'd be doing homogeneous sampling, and we'd be calculating the potential of mean force, and we can calculate interaction energy in that terms. So would you go to next slide, please? I think we're running out of time. Okay, so one more thing that we've been doing is with this computational fluid dynamics. So CoViD have been transferring like none other diseases. Like, so what is that transmission factor. It's the droplets, right? The sneezing droplets or the spit droplets. So that is something that we can make a good study of. So typically, computational fluid dynamics is like we can predict the flow of the fluids and simulate such systems in that record. Like suppose if this can be applicable, like this thing. This is one of the case that we have been trying to run. We've been using TPM foam solvers for that. So at first we'd be making mesh and let me not go to those things. Like what can be the applications? Like for an example, suppose there is an office and there is a room. So how should the seats in that room of the office be placed such that the transmission risk is the minimum? That can be of a great studies for architecturals. And the other thing can be about the designing some ventilators and simulations for designing the bioreactors, like what should be the typical, what should be the structure of the SAT says that the bioreactor can be functioning the best way, and mixing times, and we can calculate the different kind of profiles, like velocity profiles of different areas in that typical bioreactors. So these are a few of the things that I actually wanted to say. And actually my very objective of this presentation was to motivate especially students of the university to set a research culture at High Performance Computing Center. So I hope you got some information, and thank you very much. And in the next slide, the acknowledgements that I want to acknowledge. Thank you very much.
Thank you so much, Mr. Sarun sir, for your kind words, valuable thoughts, and gracious support. The exemplification you shared in your presentation was really spectacular. Despite being young and only recent graduate, both speakers have worked a great deal in battle against COVID-19, and that is something we need to appreciate. Many thanks to